In this video, I'm going to go through the formal definition for a pushdown automata. What I need you to remember is how we've defined machines in the past using tuples, and the basics of what a pushdown automata is from the previous video. So if you remember before, from the non-deterministic finite state machines, we defined them formally as a quintuple, where the first element was the set of states, the second element was the set of symbols that the machine could handle coming from the input string. The third element was a transition relation that took pairs of state and input symbol, so pairs from these crossed, and gave us the state to which we should move. We had here the start state, which was an element of the set of states, and we had here the accepting states, which were a possibly complete subset of the states. This gets augmented slightly for a pushdown automata into a six-tuple. So what we have is that we have the exact same sets for the set of states, the input alphabet, the start state, and the accepting state. These definitions don't change at all. The definition for the transition relation changes, and we also get a new element, capital gamma, which is the stack alphabet. So that is the set of symbols that we can push onto and pop off of the stack. Now, in many cases in this course, it will be related to sigma and may often be a subset of sigma, but there is no formal relationship between the two. So they can be completely disjoint sets where we have the intersection of the two of them being the empty set, or one could be a subset of the other, or vice versa. Anything's really possible. So the new element that I introduced, gamma, which was the stack alphabet, is actually very simple. But the transition relation delta, capital delta, is slightly more complicated. So for non-deterministic finite state machines, the transition relationship was a subset of the following. So it was a subset of the Cartesian product of this big green thing on the left here, which was the Cartesian product of the states with the input alphabet and epsilon, and then this was Cartesian product with k. But basically what we had was elements of delta which look like this. So upon in Q0, if we see an A, we transition to Q1. And that was pretty simple. Now I've color-coded these parts because a lot of them are exactly the same when we look at a pushdown automata. So this is what we have for a PDA. So you'll note that the green part is the same. So we still have Q0 upon seeing some symbol in the input alphabet or possibly epsilon. And we still have a state over on the right-hand side that we transition into. But the big difference is that we also include these elements from gamma star. So that is, we might have something that looks like this. In Q0 with, say, an A, and at B, T, triangle, transition into Q1 and push two at symbols, though it may also be empty. So this is an example element from our transition relation. We have the state that we have to be in for this element of the transition relation to mean anything. We have the symbol that we have to see at the start of the string. Then we have the set of symbols, possibly empty, that we pop off of the top of the stack, and these have to be there in order for this transition to occur as well. And over here we have the state that we transition into, and an possibly empty or possibly very large set of symbols that we push in order back onto the stack. So here is the transition relation for the very small PDA that you saw in the last video. So you can see here that there's only 3 elements because there's only 3 transitions. And this is the first transition. We're in Q0. We're moving to Q0. We're doing so when we see an A in the string, and we don't care what is on the stack. We won't require there to be anything on the stack, and therefore we won't pop anything off the stack. But when we do move through this transition, we're going to shove an @ symbol onto the stack. This transition is nice and simple. We're in Q0 and we're going to Q1, and we don't care what's in the string or what's on the stack, and we're not going to push anything onto the stack. This final transition here is from Q1 to Q1, and it turns out I haven't color coded these very well. We're going to require that we see a B on the front of the string, and we're going to consume that. We're also going to require that there is an @ symbol on top of the stack, and we're going to pop that off. And we're not going to push anything back onto the stack. So to bring it all together, for this particular example, we have that the formal definition of the pushdown automata is this 6-tuple, where the elements of the 6-tuple are the states and the input alphabet, like we had before, nothing different. Now we also have the stack alphabet, which in this case just consists of one symbol, the @ symbol. We have the transition relation, which we described on the previous slide, and you can see how if you actually shove that into these tuple definitions, it can get pretty complicated. So we often do our tuple definition, and then we put capital delta in there, and then we define the transition relation somewhere separately to make it possible to actually read it. We have the start state, which is exactly the same as in a finite state machine, and we have the set of accepting states, which are exactly the same as we have in the finite state machine. However, keep in mind that how the machine actually accepts a string, so the conditions under which it accepts and rejects, are slightly different because we have the presence of this stack. So what you should have from this video is an understanding of the sextuple representation of a pushdown automata, and you should understand how you can go between the tuple representation and the graphical representation and vice versa.